All right, so now we're going to move on to two new other thermodynamic quantities, entropy and free energy. Again, in the weird world of energies, these are just different manifestations of energy. They're still measured in kilojoules or kcal or whatever it may be. It's just instead of being heat, they're going to be these other, have these other sort of reasonings behind them. Entropy is the weirdest one. I'm not gonna lie, it took me a long time to wrap my head around it. So I'm gonna do my best to explain it to you. The simplest way to think about entropy is the universe wants everything to be disordered. We're being pushed towards a disordered state. So in chemical reactions, in everything, randomness is going to be the most favorable. And what the heck does that mean? Let me just give some simple examples sort of outside of chemistry. So let's take this example right here. Okay, so this is meant to represent two gases that are being contained in this sort of hourglassy kind of vessel. And then I'm going to open up this stopcock. Well, what's going to happen to these two gases, right? Well, that is not what I wanted to do. They are going to mix, obviously. Okay, so we sort of all knew that that was what was going to happen, but why? Okay, it turns out that's because this is a very low entropy state, not a lot of randomness, and this is a very high entropy state, a lot of randomness. So what does that mean? Well, let's think of how we would, it sort of makes sense as to how we went this direction. But think about what would have to happen to move this direction with that stopcock opened. That means that every single one of those green balls would have to start moving in one direction. They all have to move in the same direction. And all the purple balls all have to move in the other direction. What are the chances that that's just going to happen, right? That's not going to happen by random chance, because that's how molecules move. They move in random directions. So you'd have to have some instance where it just happens that all the green molecules are moving in the same direction. And it just happens that all the purple molecules move in the same direction. That's a very ordered state, a very ordered movement. Whereas to go the other way, everybody can just move in any direction randomly, right? I mean, it's not an ordered state that you're having to deal with then. Kitty's trying to mess my lecture up. So this is this idea of this push towards randomness. Another sort of way that's, entropy is actually a very statistical quantity. So it comes up, you actually may have, you will come up across it in advanced statistics classes, as well as, working with big data and stuff like that. So it's not just in chemistry that this concept exists. And there's this idea that it's the number of states that a molecule can distribute its energy over, right? So that would indicate more randomness. So I just want to give an example of like what the heck that would mean. Again, using non-chemistry. So this is this idea of taking a quarter and flipping it 4 times, right? I think we all know that getting heads 4 times in a row is much less likely than getting 50% heads and 50% tails, right? A coin flip is 50-50. So this would be our low entropy state, whereas 50% heads and 50% tails is our high entropy state. And why is that? Because there's just more ways to get 50% heads, 50% tails than there are to get all heads, right? To get all heads, everything has to go right. You got to get heads the first time, heads the second time, heads the third time, heads the fourth time. There's only one way to do it. Well, to get 50% heads, 50% tails, I could get head, head, tail, tail, head, tail, head, tail, head, tail, tail, head, et cetera, et cetera. There's multiple states that have that same outcome as opposed to just the one, okay? So this is just, I know it's kind of a bizarre thing in terms of how we're going to translate this to molecules, but again, it's, easiest thing, think about it as just the universe liking randomness and disorder, but also the more sort of states that are available, the better the lower energy that will be. Okay, so now let's move it over to actually talking about chemistry here. When we're talking about rotation of, entropy in a molecule, what we're talking about are going to be, again, it's going to be distributed over these energy states, but here we're specifically talking about vibrational, rotational, and translational states of a molecule. okay? So first of all, bonds, they vibrate. You can also rotate about a bond. Remember all that Newman's projection stuff that we were doing last time, talking about the different rotational conformations of a molecule. And then translational is a molecule's ability to move, you know, in XYZ coordinates in space. Don't eat that. Okay. How vibrational entropy plays a role is not something we're going to be able to cover on this course. It's a very complicated quantum mechanical type calculation that you would have to do. It's not something that you can see with your eye. However, we can sort of reason just by looking at structures why they might have more rotational states available. So let's take a look at these two molecules down here. Which one do you think is going to be my low entropy state molecule, and which one's going to be the high entropy molecule? All right, so the question is, which one has more rotational states available to it? Remember, single bonds, you can rotate about them, but if you're locked in a ring here, you're sort of constrained in how much you can actually rotate, right? So for cyclohexane, we really only have those two chair conformations that we know it flips back and forth between. But in this bond over here, it can rotate about this single bond, this single bond, this single bond, this single bond, this single bond. Think about all the different Newman projections you could draw for this molecule right here, right? Those would all be representing different rotational states of that molecule. This is why a high entropy, and specifically with regard to its rotational states, and this one is low entropy. Okay, translational is another thing that we can see kind of easily. So this is most easily seen in terms of like going from 1 mole of reactant to 2 moles of products. You're increasing the number of translational states available. So what do I mean by that? When you're starting out with 1 mole of product, so for example here, we have A and B bound together. Well, everywhere in space that A goes, B has to go too. Right? So these are the different, all these different translational states that are available, but they're always together. If a reaction breaks them up, now all of a sudden they can explore space independently. So the result is more translational states are available if my reaction is generating more moles of substance, right? So this is my high entropy state. This is my low state. And so this reaction would be entropically favorable, right? Meaning that the entropy is increasing, which again is what the universe wants to do. It wants everything to be random. Another good example would be going from like a solid or liquid to a gas, right? Solids and solids especially are very, very confined translationally. Liquids are not as confined translationally, but they can't explore space quite as much. And a gas has just freedom to explore everything. So this would be, these are both examples of translational entropy. Okay, so one of the things that we're going to do is we're going to look at a chemical reaction and we're going to say to ourselves, is this reaction entropically favorable? And so one of the things we're going to be doing for is looking, does it go, for example, from a solid to a gas? Do I start out with 1 mole of substance and generate 2 moles of substance? That would be an indication. Those are both, again, translational entropies. What about if I start out with a cyclic compound and my chemical reaction breaks it up into an acyclic compound? This is, again, entropically favorable. I have my low entropy state here, and my high entropy state here. And this has everything to do with rotational entropy, right? Again, like we said on the previous slide, these cyclic compounds are confined in how much their single bonds are allowed to rotate, whereas this one here is free to rotate about all of these. So again, I would look at a reaction like this where a ring is being broken, and I would say, aha, that is an entropically favorable reaction. Another common example that we're going to see is converting an alkene to an alkane. Is this translational or rotational that's going to be, translational entropy or rotational entropy? So this is again, my low entropy state. This is high entropy. And this is, again, has everything to do with rotational entropy. Because although both of these have these two single bonds that can be rotated about, remember, you can't rotate about a double bond. Because of how the pi bonds are, you can't just sort of rotate about them. So this would have less so my alkene has less rotational states available to it. We can actually, I mean, just to sort of take it a step further, if we wanted to draw like a Newman projection for an alkene, so now I'm going to look down this double bond here. Remember that one of the things about an alkene is that all of these atoms, including these hydrogens that are here, all lie in the same plane, right? So if I was going to draw a Newman projection of an alkene, here's my front carbon corresponding to this guy here. Got a methyl group on one side and a hydrogen on the other. Now I'm going to draw in my back carbon. It also has a hydrogen. And those are permanently in this eclipsed conformation. And this is the only rotational state that's available to that double bond. It can't move from this one. Whereas if we were going to draw our alkene, this is just one of several rotational conformations that we can draw, right? Remember, again, back to that whole, your challenge problem from last week, for example. Oh, no, I guess 2 weeks ago. Anyways, you can use these Newman projections to draw all these different rotational conformations for this state, right? So again, energy distributed over multiple states. In this case, we're talking about rotational states. Okay. All right, so now Gibbs free energy. So we're going to see how entropy and enthalpy combine to give you Gibbs free energy, or I just call it free energy. Gibbs is the dude who theorized it. Apparently was a really weird dude. Anyways, what I want you to think about when you think about Gibbs free energy, right? So when you think of enthalpy, you think of what? Heat. When you think of entropy, you think of what? Randomness or disorder. When you think of free energy in my mind is, does the reaction happen? Does the reaction happen or not? Another way that we would say this is does the reaction occur spontaneously or non-spontaneously, meaning it doesn't occur? So this is what your free energy is really telling you. So negative free energy is what we call an exergonic reaction. And these are going to be spontaneously favorable to the products, meaning they will move in the forward direction, without you really having to do anything. Okay, so that's a negative delta G. This is the same energy type of diagrams that we were showing before, except for now on my x-axis is free energy instead of enthalpy. But you notice the sort of pattern of an exergonic and an exothermic reaction, right? It means that the free energy of my reactants was greater than the free energy of my products. And then the difference here is that delta G, and in this case it's negative, so this reaction will occur spontaneously. A non-spontaneous reaction, an endergonic reaction, this is one that would favor the reactants, okay? And this is when your reactants free energy is lower than the product's free energy. So that delta G is positive. So that's what your delta G is telling you. Does this reaction occur or not? So how do we use this sort of information qualitatively? So this is going to be our example reaction here. And we're going to try to figure out whether or not this reaction occurs spontaneously, or under what conditions it would occur spontaneously. So for that, we need to know the relationship between Gibbs free energy, enthalpy, and entropy. So take a look at this reaction here. Enthalpy plus negative temperature times entropy, or change in entropy, is what's going to give you your Gibbs free energy, right? And we want, well, for a reaction to occur spontaneously, the Gibbs free energy needs to be negative. So it's all about the sign, plus or minus, of these factors here. I should say that when I was saying a high entropy state, going from a low entropy state to a high entropy state, which is good, that means that you have a positive delta S. Okay, so first thing we want to do is predict the sign for delta S in this reaction here. Where I have this diene here mixing with this ethene here to create this cyclic compound. Well, what do you think is going to, if you had to predict the sign of delta S, and I guess to make it easier, so positive means entropically favorable, and negative means unfavorable in terms of entropy. So do you think this reaction is going to be entropically favorable or unfavorable? Well, first of all, you are going from 2 moles of reactants to just 1 mole of products. So you're going to take a hit in terms of the translational entropy there. Not only that, but you're creating this cyclic compound. So you can't really rotate about these double bonds, except for this one. But now you've created this cyclic compound, which has very constrained rotational states. So this would be an entropically unfavorable reaction, which means that the delta S is going to be negative. Okay, so now let's look at trying to determine the sign for the delta H. Well, notice here what's being broken and what's being formed. I have 1, 2, 3 pi bonds that are going to be on my reactant side, and 1, 2, 3, 4 sigma bonds. And on my product side, I have 1, 2, 3, 4, 5, 6 sigma bonds and 1 pi bond. Okay, so how does that help you predict delta H? Hopefully you guys, from your assignment from the enthalpy assignment, remember that pi bonds are weaker than sigma bonds. So if I have more pi bonds over on my reactant side and then more sigma bonds on my product side, that's an enthalpically favorable or an exothermic reaction. The formation of those sigma bonds is going to release more energy than it took to break those pi bonds. So this is going to have a negative delta H, right? That will be an exothermic reaction. So then if I look, how does that affect what I would get for delta G? So first of all, notice that there's this negative sign in front of temperature here. So that's going to take that negative delta S, and then I'm going to multiply it by negative temperature, and it's going to become positive again, right? So this whole term is going to end up being positive. So you see that I have this like push and pull that's going on here. On the one hand, I have my enthalpy values that are negative. That's going to sort of like be driving that reaction in terms of making delta G negative. But then I have this positive component for the entropy. So now this is where the role of temperature comes in. If the T value in here was really low, then this portion of this equation would be negligible, and the enthalpy would rule, and this reaction would be favorable. So this would be favorable at low temperatures. But then as I increase temperature, this term becomes more and more important. And so that means that it would become unfavorable at high temperatures. All right, so that's how qualitatively we can sort of predict whether or not a reaction will occur, right? Using what we know about bond strengths, as well as what we sort of just learned about how we can predict whether or not a reaction will be entropically favorable, we can combine those into our Gibbs equation here, free energy equation, to determine whether or not a reaction will be spontaneous. I guess I should use the word, let's use that word, spontaneous at low temperatures and non-spontaneous at higher temperatures. Okay?